In this question, a parallel plate capacitor is connected across a 2-volt battery and charged. The battery is then disconnected and a glass slab is introduced between plates. Which of the following pairs of quantities decreases? So here in this particular case, just have a look in this particular figure. So if we just see this particular figure over here, assume that these are parallel plate capacitors, clear, and space between them is completely free space, or you can say it is a vacuum. Nothing is present in between the plates, and suppose this is a 2-volt, this is a 2-volt, this is a 2-volt battery which is connected over here, and this is charged. Suppose if this is charged, that means suppose this upper plate will get positively charged and this lower plate will get negatively charged, as the upper plate is connected to the positive terminal of the battery and lower plate is connected to the negative terminal of the battery. So right now here in this particular case, the plates are charged over here, and after that the battery is disconnected and glass slab is introduced between the plates. Right now what will happen, we'll disconnect this charged capacitor. These charged capacitors are disconnected right now, and after that what we'll do, we'll introduce this glass slab. So this just think that this is a glass slab which is now introduced between the plates. Then what will happen, which of the following pair of quantity decreases? So here in this particular case, so as the plates are already charged, and by assuming the law of conservation of charge, that means here even after inserting the dielectric material, or you can say inserting the glass slab, the charge stored across the plates will remain as it is. Clear? Charge will remain constant, no change in the value of charge after inserting the dielectric or glass slab. Clear? And so charge is constant. Then what about the capacitance? So initially the capacitance was C. Initially the capacitance could be defined as epsilon naught A divided by D. So then after inserting the dielectric material, so capacitance will increase by K times. Clear? So it will be Kc. And so capacitance over here, that means here what about the capacitance? Capacitance generally increases. Clear? As you insert the dielectric material. So as we insert the dielectric material, then capacitance increases. Then what about the potential? Clear? So potential difference across the plates. So V equal to Q by C, as in these three variables. So Q is constant over here, that means charge that is constant over here, and C increases, that means potential will decrease. So here in this particular case, potential decreases first, capacitance increases. And next one is about energy. Clear? Energy stored across the plates of the capacitor. We know the formula for energy stored is it can be defined as two types. It is half CV square. We can use this formula, or we can use Q square by 2C, or we can use another formula, that is half QB. So here in this particular case, in order to define the energy stored, here in this particular case we'll be using this formula Q square by 2C, because here in this particular case, as Q is constant, and that means the upper numerator part will remain constant as it is. That means, but capacitance is increasing after inserting the dielectric material. So as capacitance is increasing, that means energy stored across the plates of the capacitor will decrease. That means here in this particular case, the two parameters that will decrease is potential difference as well as energy stored across the plates of the capacitor. So these two will decrease. So we'll check the options, charge and potential. Potential difference, yes, which that will decrease, but charge will remain constant. So that is not potential difference and energy stored. So both these two will decrease over here. So that means option B will be the correct one. And option C, energy stored and capacitance over here increases, so that will not, but energy stored decreases, that is correct. So and option D, capacitance and charge, capacitance increases and charge remains constant, that will not. So option B will be the correct one. In this question, a capacitor has some dielectric between its plates, and the capacitor is connected to a DC source. The battery is now disconnected and then the dielectric is removed. Then which of the following will be correct? So here in this particular case, so what it is saying is that initially a capacitor is having a dielectric between its plates and it is connected to a DC source. पहले से एक कैपेसिटर है जिसके अंदर में डायरेक्टिक मटेरियल प्रेजेंट है और वो डीसी सोर्स के साथ कनेक्टेड है. एंड आफ्टर दैट इज व्हाट उसके बाद बैटरी को डिस्कनेक्ट कर दिया जाता है एंड डायरेक्टली उसको वो भी रिमूव किया जाता है। तो कौन सा यहाँ पे सही होगा? So in this particular case, if we just look at a figure, so here in this particular case, just assume that this is a dielectric material, red color one box type. It is a dielectric material, and these are two parallel plates capacitor. So here in this particular case, assume that we are inserting this dielectric material in between the plates. Clear? And right now it is assume that it is charged. So it is charged means that means the plates will, as the upper plate is connected to the positive terminal, so it will get positively charged, and the lower plate is connected to the negative terminal, so it is negatively charged. So finally, and right now what we will be doing, as it is overall it is getting charged, and the net potential difference right now over here is V, same as the potential across the cell. तो अभी ये जो दो प्लेट्स और उसके अंदर में जो डायलेक्ट्रिक है, इनके बीच में पोटेंशियल डिफरेंस अभी कितना होगा? सेम एज द potential difference of the battery or cell. So right now what we'll be doing, we'll be disconnecting the capacitor system. So we are disconnecting the whole system. So right now that means here in this particular case, what will happen, here it is said that battery is disconnected, but यहाँ पे हम समझने के लिए मान लेते हैं कि अभी सिस्टम से ये डिस्कनेक्ट हो गया. That means this capacitor will remain charged as it is. जितना चार्ज वहाँ पे था उतना ही चार्ज रहेगा. दैट मीन्स Q विल रिमेन कांस्टेंट. चार्ज यहाँ पे कांस्टेंट रहेगा. क्लियर? क्योंकि यहाँ पे और कोई दूसरा सिस्टम के साथ ये कनेक्टेड नहीं है. तब अगर कनेक्टेड होता तो वहाँ पे क्या होता? डिस्चार्जिंग प्रोसेस होता. सो चार्ज विल रिमेन कांस्टेंट, एंड इफ चार्ज रिमेन्स कांस्टेंट, then after that what we'll do, the next step is that we'll remove this dielectric material. So here if we'll remove, assume that just here we'll remove this dielectric material. Here we have removed this one. Clear? So right now what will happen, so once after removing, that means here initially the capacitance with dielectric, initially assume that the capacitance with dielectric was C. Clear? That means initial capacitance is C. Then what will be the capacitance when the dielectric when the material is removed having dielectric constant K? Assume the material is having dielectric constant K. Then what will be the final capacitance right now over here? That means it will decrease by K times. Clear? So this capacitance which is the initial capacitance जो पहले से था, वो capacitance क्या होगा? वो अभी डिक्रीज होगा. क्लियर? तो अगर वो कैपेसिटेंस यहाँ पे डिक्रीज हो रहा है, कैपेसिटेंस अगर यहाँ पे डिक्रीज हो रहा है, देन चार्ज तो यहाँ पे कांस्टेंट रहेगा, ये इसमें कोई चेंजेस नहीं आएगा. क्लियर? सो तो फाइनली व्हाट अबाउट द पोटेंशियल डिफरेंस? सो पोटेंशियल डिफरेंस, इनिशियल पोटेंशियल डिफरेंस यहाँ पे कितना है? V है. देन व्हाट विल बी द फाइनल पोटेंशियल डिफरेंस? तो अभी कितना पोटेंशियल डिफरेंस होगा? तो दैट मीन्स दैट विल बी इक्वल टू Q बाई C. सो Q बाई C इज, दैट मीन्स इट इज द फाइनल कैपेसिटेंस. क्लियर? सो फाइनल कैपेसिटेंस जो है वो तो यहाँ पे डिक्रीज हो रहा है. क्लियर? दैट वैल्यू इज डिक्रीजिंग, दिस कैपेसिटेंस इज डिक्रीजिंग ओवर हियर. दैट मीन्स द पोटेंशियल डिफरेंस राइट नाउ विदाउट द डायलेक्ट्रिक मटेरियल दैट विल इंक्रीज. क्लियर? सो कैपेसिटेंस यहाँ पे क्या हो रहा है? फाइनल जो कैपेसिटेंस वो डिक्रीज हो रहा है, तो पोटेंशियल डिफरेंस क्या होगा? पोटेंशियल डिफरेंस में चेंजेस आएगा. तो कितना चेंजेस आएगा वो तो मैग्नीट्यूड हमें वैल्यू अगर दिया तो हम कैलकुलेट कर लेते हैं. तो यहाँ पे बस इतना ही है कि चार्ज यहाँ पे Q रिमेन्स कांस्टेंट और पोटेंशियल डिफरेंस इस वाले सिचुएशन में क्या होगा? वो इंक्रीज हो रहा है. क्लियर? अच्छा, पोटेंशियल डिफरेंस अगर इंक्रीज हो रहा है तो उसके साथ हमारा और भी एक चीज है यहाँ पे, कैपेसिटेंस पहले से ही है कि वो क्या हो रहा है? कैपेसिटेंस इज डिक्रीजिंग. क्लियर? पोटेंशियल डिफरेंस इंक्रीजिंग, कैपेसिटेंस डिक्रीजिंग. एंड व्हाट अबाउट द एनर्जी स्टोर्ड? एनर्जी स्टोर्ड इसको हम कैसे कैलकुलेट करेंगे? तो एनर्जी स्टोर का जो फॉर्मूला हम यहाँ पे अप्लाई करेंगे, तो हम यहाँ पे अगर हाफ C V स्क्वायर अप्लाई करेंगे तो वहाँ पे C डिक्रीज हो रहा है, V इंक्रीज हो रहा है, तो इसमें कैलकुलेट करना थोड़ा डिफिकल्ट होगा. तो हम कौन सा फॉर्मूला यहाँ पे अप्लाई करेंगे? विल बी यूजिंग Q स्क्वायर बाई 2C. सो हियर इन दिस पर्टिकुलर केस एज कैपेसिटेंस इज डिक्रीजिंग, so potential energy stored will be increasing. So here in this particular case energy stored will increase. So that means here we can say that these are the changes. These are the changes that will take place after removal of dielectric material from the charged capacitor. So here in this particular case, capacitance will increase, but it is saying decrease, so this will be wrong. Energy stored will decrease, energy stored is increasing, that is also wrong. Electric field will increase, electric field यहाँ पे हम लोग नहीं लिखे हैं, तो electric field को हम देख लेते हैं. तो इसमें अगर electric field E को हम कैलकुलेट करेंगे तो electric field क्या होगा? So here in this particular case, E equal to V by D. Clear? तो इसमें distance between the plates that is not changing by when we take out the dielectric material. तो distance यहाँ पे constant है, तो potential difference वो क्या हो रहा है? Increase हो रहा है. As potential difference is increasing, that means electric field will increase. That means here in this particular case, electric field will also increase. So electric field increases, so this is option C is correct, and voltage will decrease. Voltage is increasing, so option D will be wrong. So option C in this particular question will be correct. In this question, a capacitor of capacitance 700 picofarad is charged by 100 volt battery. The electrostatic energy stored by the capacitor is. So here in this particular question, capacitance which is given over here is 700 picofarad. So 700 into 10 to the power minus 12 farad. And voltage supplied is 100 volt. So finally, what will be the energy stored across the capacitor? So energy stored will be nothing but U equal to half C V square. So half capacitance is 700 into 10 to the power minus 12 into voltage supply is 100 square. So finally over here, so how much will be getting? So 2, and this one will be 350. So it will be 10 to the power 350 into 10 to the power minus 12 into 10 to the power 2, and its square will be 10 to the power 4. So it will be 350 into 10 to the power minus 8. So energy stored will be 350 into 10 to the power minus 8 joule, or if we just try to write, so it will be 3.5 into 10 to the power minus 6. So just dividing and multiplying by 100, so how much will get? 3.5 into 10 to the power minus 6 joules. So option A 2.5, option B 3.5 into 10 to the power minus 6. So option B will be the correct one. C is wrong and D is also wrong, so it is 10 to the power minus 4. In this question, a 16 picofarad capacitor is connected to 80 volt supply. When capacitor is fully charged, the amount of electric energy stored in it. So here in this particular case, the capacitance is given 16 picofarad. So it will be 16 into 10 to the power minus 12 farad. And the potential difference is given 80 volt. So finally what is asking, capacitor will fully charged, the amount of energy stored. So what will the amount of energy stored when the capacitor gets fully charged? So amount of energy stored is how much? It will be half C V square. As capacitance is given and potential difference is given, so we'll be using this formula. So half capacitance is 16 into 10 to the power minus 12 into potential difference is 80, so it will be 80 square. So we can write 80 into 80. So we can cut this one by 8. So here in this particular case, what will be getting? So 8 into 8 into 8. So 8 is 64. 64 8 it will be 3. So it will be 2. So 51 512. So it will be 512 into 10 to the power minus 12 into 10 to the power 2, because these two zeros, that means here we have taken 8, so it will remain remaining is 10 is, so it will be 100. So finally how much will be getting? 512 into 10 to the power minus 10. So that value will, so dividing and multiplying by 100, so how much will get? Will get 5.12 into 10 to the power minus 8. So 5.12 into 10 to the power minus 8 joule will be the correct answer. So here 4.5 wrong, option B 5.1 into 10 to the minus 8 joules, so option B will be the correct, and option C this is 2.5, option D 3.2 wrong. So finally option B will be the correct one. In this question, a capacitor is charged through a potential difference of 200 volt. When 0.1 coulomb charge is stored in it, the amount of energy released by it when it is discharged. So here in this particular case, the potential difference that is given is 200 volt across the plates of capacitor, and charge given is simply 0.1 coulomb. So, and this is the charge which is stored during charging of capacitors. So that means what is asking? Amount of energy released when it is discharged. So what is the energy stored during charging? So energy, we first calculate energy stored during charging. So energy stored during charging will be simply how much? It will be U equal to half Q into V. So half of Q is how much? 0.1 into potential difference is 200 volt. So 2, so it will cut, so by, so it will be 100, so it will be 10 joule. So energy stored during charging is 100 joule. That means what will be the energy released when it is discharged? So this is 10 joules of energy it's needed from, or you can say 10 joules of energy is stored in between the plates of capacitor when we connect it through a 200 volt supply to store a charge of 0.1 coulomb. Clear? So that means energy released when the capacitor gets completely discharged will be same as energy stored during charging. So ये जो value है ये कितना होगा? Will be same as U. That means it will be 10 joules. So 10 joules of energy will be released. So option B will be the correct answer. In this question, a parallel plate capacitor has a uniform electric field E in the space between the plates. If the distance between the plates is D and area of each plate is A, the energy stored in the capacitor is. So here in this particular case, if we just look at this particular figure over here, so here we'll remove this one. So here this is a parallel plate capacitor, and here in this parallel plate capacitor, the plates are having area A. Area of the plates are A, so it's also having area A, and distance between the plates is D over here. So finally, what will be the capacitance of this parallel plate capacitor when it is capacitance will be how much? It will be epsilon naught A divided by D. And as we connect this to a say external cells or external source or external supply, then what will happen? This will get charged. So this upper plate will get positively charged and the lower plate will get negatively charged. So finally what will happen? So equal amount of positive and negative charges will arise over here. So it will be negatively charged and the upper one will be positively charged. So here in this particular case, what we'll found the electric field will be in between the plates of capacitor. Electric field will be in between the plates of capacitor. This is how it looks like. Clear? So if this electric field arises over here, then what is the magnitude of this electric field in between the plates of capacitor? So here in this particular case, we know that magnitude of E equal to nothing but dV by dr, or as potential difference across the plates of capacitor is same as the source potential, so it will remain V by distance between the plates, let it be D. So finally E will be nothing but V by D. So capacitance is epsilon A by D and E equal to V by D. So finally what will be the value of V over here? So value of V will be equal to simply E to D. So then it is asking about energy stored in the capacitor. So the value of energy stored will be, energy stored is indicated by U. It will be nothing but half C V square. So half C is epsilon naught A divided by D and V is ED. So it will be ED whole square. So finally it will be half epsilon naught A divided by d, and it will be E square d square. So d got cancelled out. So finally, how much will be getting? Half epsilon naught E square A into d. Clear? So finally, this will be the energy stored in the capacitor. So option A, it is half epsilon, it is the energy, and this is so finally it is the energy density, and option B is something divided by epsilon naught, so that is also wrong. Here is wrong. C is half epsilon naught E square AD, so option C is the correct one. And here it is only epsilon naught E square AD, half is not there, so this will be wrong. So option C is the correct one. In this question, a metallic sphere of radius 18 cm has been given a charge of 5 into 10 to the minus 6 coulomb. The energy of the charged conductor is. So here in this particular case, assume this is a metallic sphere. This is a metallic sphere whose radius is given 18 centimeter. Clear? And it is given some charge. How much charge? So it will be 5 into 10 to the power minus 6 coulomb. So 5 microcoulomb charge. So it is a positive charge. So these positive charges will be distributed uniformly all over on the surface of the given metallic sphere. Clear? So if it is the case, then what will be the energy of the charged capacitor? We know that the formula for energy is nothing but it can be written as half Q into V, or we can use the formula half CV square, or it can be half Q square by C, or Q square by 2C. We can use any formula. So if we just look over here, so suppose here in this particular case we'll be using this first formula. If we'll be using, so energy will be how much? It will be half Q is how much? Q is 5 into 10 to the power minus 6. And what will the potential difference? So here in this particular case, if we calculate the potential difference, or you can say the voltage, or you can say potential of this given metallic sphere, it will be how much? It will be KQ by R. As this is a conducting type of sphere, metallic sphere, so potential it will behave as a equipotential surface. That means potential inside or on the surface it will remain constant. So that value will be 9 into 10 to the power 9 into Q is 5 into 10 to the power minus 6 divided by radius is 18 into 10 to the power minus 2 meter. So finally the value will get, so 9 to the 18, so it will be 2.5 into 10 to the power. So here 2 if goes minus 2 is goes up, so it will be 10 to the power 11, so it will be 11 minus 6, so it will be 10 to the power 5. Clear? So 2.5 into 10 to the power 5 volt of potential. So finally if we put that value over here, so it will be 2.5 into 10 to the power 5. So that value will comes out to be so if we cut this, so it will be 2.5. So 2.5 into 2.5 will be 6.25 into 10 to the minus 6 plus 5, it will be 10 to the power minus 1, or that means 6.25 divided by 10, so it will be 0.625 joules. Clear? So you can use this formula, or you can use capacitance. So first of all, if you use CV square formula, so already we got the value of potential. So we need to find out the capacitance, and just if you multiply them, then also we'll get the same result. And also you can use the formula Q square by 2C. So what we need to do over here is that if we use these two formula, then first of all we need to calculate the capacitance. Capacitance of this spherical type of metallic sphere will be how much? So इसका formula है 4 pi epsilon naught into R. So 4 pi epsilon naught is nothing but 1 by 9 into 10 to the power 9, and the radius is 18 into 10 to the power minus 2. So 9 to the 18, so it will be 2 into 10 to the power minus 11. So we got the value of capacitance, that means energy stored. That means over here the energy stored U is equal to half CV square. That formula if we apply, so half into C is 2 into 10 to the power minus 11 into V square. V square, that means 2.5 into 10 to the power 5 square. So finally this two will get cancel out. So here how much we'll get? 2.5 square, that means it will be 6.25, and 10 to the minus 11, and here it is 10 to the 10, so it will be 10 to the minus 1, 10 to the minus 1, so same result will get 0.625 joule. So finally this will be a process. This is a process where you have to calculate the capacitance separately, so it will be better to go through this one. Clear? Or you can use this formula q square by 2c, then also you will get the same result. Clear? So finally here option B will be the correct one. In this question, two spherical conductors, each of capacity C, are charged to potential V and minus V. These are then connected by means of a fine wire. The loss of energy. So here in this particular case, what it's saying is that there are two conductors. Let it be C1 and C2. So these two conductors are like this. These are insulating strands. Clear? So here in this particular case, just remember that these are over here. These orange colors are, these are insulating strands. So here this is conductor. These are two spherical conductors. Clear? And assume that one is having potential V and another one is having potential minus V. Here these are what? These are orange color ones are insulating strands. Insulating strands. And right after that, what is saying? These are connected by means of a fine wire. So here in this particular case, if we assume that we are connecting these two spheres by means of a wire. So initial potentials are given, and these are connected by means of a fine wire. So what? Just another figure of this one. The situation will be the situation that this is the initial situation. This is the initial situation over here. Initially, these two are present separately, having potentials V and minus V, and right after that, what will happen? After some time, we will connect these two. Clear? So if we will connect these two, that means what will happen? Charges will move from higher potential to lower potential surface or region here. So charges will move from left to right. It will move like this. Clear? If it is moved like this, then what will be the potential? What will be the situation over here? So here what the concept is that when we connect such type of systems which are already charged, then finally what will happen? They will achieve a common potential. That means till how long the charge will flow from higher potential region to lower potential region till the potentials remain same. So assume that the final potentials be V prime each. So here in this particular case, we'll here the final situation will be this one. That means when both the spheres which are charged, when they are connected, then charges will flow from the higher potential surface to the lower potential surface till their potential becomes same. जब तक उनका potential same हो जाएगा तब तक charge flow होगा, and once they achieve the common potential, after that there will be no flow of charge. Clear? That means flow of charge will cease. So here in this particular case, what is asking? The loss of energy. So in this particular case over here, if we just calculate the initial potential energy of the system, तो ये initial system है और ये आपका final system है. Clear? तो initial system का जो energy होगा, U initial will be how much? It will be half. It will be initial energies of common initial energy of both the sphere individually. तो ये जो पहला वाला स्पीयर है, इसका कैपेसिटेंस मान लो कि यहाँ पे बोला गया कि स्पेरिकल कैपेसिटी ईच ऑफ कैपेसिटी सी, तो इसका भी कैपेसिटेंस सी है और इसका भी सी है, ये भी सी रहेगा क्योंकि स्पीयर में कोई चेंजेस नहीं है. क्लियर? सो इट विल बी हाफ सी वी स्क्वायर फॉर द फर्स्ट वन, एंड फॉर द सेकेंड वन इट विल बी हाफ सी माइनस वी square. So how much will be getting? It will be getting half CV square plus half CV square. It will be CV square. So initial energy stored across the given system separately the energy stored, or you can say total energy stored at the initial stage. And here in this particular case, once they are connected, then what will the final energy stored? Here we can calculate. So before calculating, we need to find out the common potential. What will be the value of common potential? the value or you can say the common potential achieved by both the spheres will be nothing but total charge divided by total capacitance. Total charge divided by total capacitance. Total charge is individual charges Q1 plus Q2 divided by total capacitance is C1 plus C2. So but C1 and C2 are C each. So and what is the total charge that is initially which is present in the given spheres? Initial charges is CE plus C minus V. Clear? So it will be divided by C1 plus C2, that means it will be 2C. So how much will be getting? We will be getting CV minus CV divided by 2C. So these two will get cancelled out, so finally it will be 0. So the common potential, if it is indicated by V prime, so that common potential will be how much? That common potential will be 0 over here. If the common potential is 0, that means the final energy stored across both the you can say across the system, whole system which is connected, that will be how much? That will be the energy stored in the first plus energy stored in the second sphere. So energy stored in the first sphere will be half, capacitance is not changing, and common potential we have to take, so it will be V prime square plus half, capacitance of the second sphere is C, and potential of the sphere is V prime, so that's square. But V prime is 0 over here, so these two will get cancelled out. So finally the final potential energy stored, or you can say final energy stored across the connected system will be 0, and initial energy stored across the connected system is, or initial energy present in the disconnected system, or you can say which are not connected. This is the initial energy of the system, initial energy of the system. That means this is not connected, or you can say before connection, and this is the energy of the system, final energy of the system after connection. So that is coming out to be 0. So that means what we'll be doing over here, we want to calculate the loss of energy. So loss of energy. So remember, initially it is having higher energy, and finally after connecting them we are getting less energy. So loss of energy will be always U initial minus U final. Clear? So U initial is CV square minus 0, so it will be CV square. So this will be the loss of energy. Loss of energy, how much will be getting? CV square. Here in this particular case we can use another formula. Here another direct formula we can use over here. And what is be that direct formula over here? So loss of energy, formula for loss of energy, let it be delta U. So loss of energy will be, formula will be half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. This is the formula for loss of energy. You can check my derivation for loss of energy. So here in this particular case, what are C1 C2? So C1 C2 is the capacitance of individual spherical individual metallic spheres. So C1 equal to C2, both are same given here. And potential V1 is let it be V, and V2 is let it be minus V. So if we put all these values over here, so and loss of energy will be equal to half C1 C2, that means it will be C into C, that means C square divided by 2C whole into, here V1 is V minus minus plus, it will be V. So V plus V whole square. So here how much will be getting? We'll be getting, so C, 1C will get cancel. So it will be 1 by 4, that means it will be C by 4, V plus V, that's 2V, so 4V square. So 4 will get cancelled out. So finally how much will be getting? It will be CV square. So always remember, here in this particular case, don't get confused that V1 minus V2. Suppose here if we have interchanged the values, suppose if we take V1 equal to minus V and V2 equal to plus V, suppose here if we will change, so don't get confused, it will be always positive, because even if negative sign will come, so square will be positive. So here loss of energy is coming out how much, it will be CV square. You can use the direct formula, ये direct formula आप लोग यहाँ पे इसको याद कर सकते हो, ये वाला formula loss of energy का, clear? So CV square, so here if you check, so 0 that is wrong, B wrong, and C is CV square, that is correct, 2B CV square is wrong. So option C will be the correct one. In this question, two condenser, one of capacity C and other of capacity C by 2 are connected to V volt battery. So here this is one condenser, or you can say capacitor, which is C, having capacitance C, and another capacitor here which is having capacitance C by 2 connected to this V volt battery. There this is the positive terminal and here it is negative terminal of the battery. As shown in the figure, the work done in fully charging both the condensers is, so what is the work done? So here in this particular case, as these two capacitors are connected in parallel across a battery, so that means the potential difference, or you can say potential difference across both the capacitors will be same as the potential of the, or you can say potential difference across the battery. So it will, potential difference over the capacitance C will be V, and here also potential difference will be V. So if both are having same potentials, that means what will be the energy stored across this particular capacitor? So energy stored here will be half CV square, and energy stored over here will be half, capacitance is C by 2 and potential is V square. So that value will be equal to CV square by 4. So that means the total energy, or you can say what is the work done in fully charging both the condensers. So work done, total work done will be stored as total energy in the system. So that will be calculated by using total energy. That means how much that one will be? It will be half CV square plus 1 by 4 CV square. So it will be approximately, if we take LCM and take CV square outside, it will be 4. So 4, it will be 2 plus 1. So it will be 3 by 4 CV square. So here 1 by 4 wrong, this is C, 3 by 4 CV square correct, and here it is half and here it is 2. So that means option B will be the correct one. Here also you can calculate the equivalent capacitance. There is another method where you can calculate the equivalent capacitance. Equivalent capacitance will be how much? C plus C by 2, as both are connected in parallel, so it will be 3 by 2 C. Clear? Equivalent capacitance is coming out to be how much? 3 by 2 C. That means energy stored will be equal to half C equivalent V square, because the equivalent capacitance is 3 by 2 C, which is connected across the V volt supply. So it will be half 3 by 2 C into V square. So it will be 3 by 4 C V square. So anyhow we will get the same result. In this question, a parallel plate condenser with a dielectric constant K between the plates has a capacity C and is charged to a potential V volts. The dielectric slab is slowly removed between the plates and reinserted. That means this is a single process. Clear? Removal and re-entry of reinserting of dielectric material is a single process. Clear? So then the net work done by the system in the process. So here in this particular case, if you that means here in this particular case, just think that the initial system is the initial system. Already a dielectric material is inserted between the plates of capacitor. Clear? So as it is inserted, and what it is saying that the capacitance of this system, the capacitance of this system is how much? Capacitance of this system is C. Clear? And potential difference is how much? It is said that V. तो ये जो प्लेट्स और डायलेक्ट्रिक मटेरियल प्रेजेंट है, तो इस सिस्टम का भी पोटेंशियल डिफरेंस V बोला गया है और इस सिस्टम का कैपेसिटेंस है C. क्लियर? And right after that, what they are saying is that they are saying that slowly this dielectric material will be removed. It will be removed like this, और ये कहीं पे रुकना नहीं है. क्लियर? और फिर हम उसको क्या करेंगे? अंदर ले जाएंगे। क्लियर? तो मतलब यहाँ पे फाइनली यहाँ पे रेस्ट में आएंगे। पहले से ऑलरेडी ये यहाँ पे ऐसे रेस्ट में है, तो इसका इनिशियल एनर्जी कितना होगा? तो इनिशियल एनर्जी विल बी हाउ मच? हाफ सी वी स्क्वायर। तो इसका इनिशियल एनर्जी कितना होगा? हाफ सी वी स्क्वायर। अब इसके बाद क्या होगा? जब फाइनल है, फाइनल सिस्टम कैसा होगा? क्लियर? तो फाइनल सिस्टम मान लो कि इसी को हम, ये जो सिस्टम है फाइनल में क्या हो रहा है ये, कि ऑलरेडी तो ये सिस्टम है, ऑलरेडी इसका कैपेसिटेंस सी और पोटेंशियल डिफरेंस भी है। तो अभी यहाँ पे ये जो डाइलेक्ट्रिक मटेरियल को बोला जा रहा है कि ये जो डाइलेक्ट्रिक मटेरियल है इसको हमें बाहर लेना है, ये प्रोसेस, और फिर अंदर ले आना है। क्लियर? बाहर लेके फिर अंदर। तो इस जो ये जो प्रोसेस यहाँ पे हो रहा है, बाहर ले रहे हैं और अंदर ला रहे हैं, तो ये एक ही प्रोसेस है। क्लियर? ऐसा नहीं कि हम बाहर में लेके यहाँ पे रख दे रहे हैं। क्लियर? तो बाहर में लेके ऐसे रख देने के बाद जो वाटन होगा या फिर जो चेंज इन एनर्जी होगा वो अलग होगा। क्लियर? लेकिन यहाँ पे क्या हो रहा है, इसको ऐसे बोला जा रहा है कि पहले ऐसे था, रेस्ट में था यहाँ पे, और फिर बाहर ले रहे हैं और ले आ रहे हैं अंदर। क्लियर? यहाँ पे ऐसे रख नहीं रहे, रखने के बाद 5 सेकंड बाद फिर इसको हिला रहे नहीं, स्लोली इसको हमें बाहर ऐसे ले जाना है और फिर अंदर ले आना है। क्लियर? और फिर रख देना है उसको सही जगह पर। तो अभी ये हो गया हमारा फाइनल सिस्टम। सो दिस इज द इनिशियल सिस्टम, ये इनिशियल सिस्टम है, दिस इज इनिशियल एंड दिस विल बी द फाइनल। ये अभी हमारा फाइनल है। क्लियर? तो अभी फाइनल में तो कैपेसिटेंस उतना ही रहेगा। क्लियर? अगर मान लो कि ये सिस्टम है, अगर मान लो कि कुछ ऐसा बोला गया, क्लियर, ये वाला सिस्टम मान लो कि हियर इन दिस पर्टिकुलर केस इफ, अगर यहाँ में कुछ ऐसा बोला गया होता कि ये जो डाइलेक्ट्रिक मटेरियल यहाँ पे है इसको ऐसे बाहर रख दिया गया है। क्लियर? तो ऐसे बाहर रख दिया गया यहाँ पे, ये वाला सिस्टम, तो शायद यहाँ पे क्या होगा? तो इस वाले पर्टिकुलर केस में यहाँ पे अगर ऐसा केस है तो यहाँ पे ये जो कैपेसिटेंस है, दिस कैपेसिटेंस विल डिक्रीज बाय के टाइम्स। क्लियर? तो यहाँ पे के जो है डाइलेक्ट्रिक मटेरियल का जो डाइलेक्ट्रिक कांस्टेंट है, तो उसको बाहर निकालने से क्या होगा? कैपेसिटेंस विल डिक्रीज बाय के टाइम्स। तो कैपेसिटेंस अगर डिक्रीज हो रहा है तो पोटेंशियल यहाँ पे दैट विल आल्सो इंक्रीज बाय के टाइम्स। क्लियर? पोटेंशियल डिफरेंस जो होगा प्लेट्स के बीच में वो बढ़ जाएगा, और कितना बढ़ेगा? के टाइम्स वो ज़्यादा होगा। क्लियर? लेकिन हमारा सिचुएशन वैसा नहीं है, हमें यहाँ पे क्वेश्चन में बोला है कि इनिशियल सिस्टम जो है और वो ही फाइनल सिस्टम है, तो कैपेसिटेंस भी उतना ही रहेगा, यहाँ पे सी रहेगा, और पोटेंशियल डिफरेंस भी उतना ही रहेगा, वी रहेगा, और फाइनल एनर्जी स्टोर्ड भी कितना होगा? दैट विल बी हाफ सी वी स्क्वायर। क्लियर? दैट विल रिमेन्स एज इट इज। That means the net work done during the system. So net work done is nothing but this is the initial potential energy and this is the final potential energy. Then difference in potential energy delta U will be, or work done will be nothing but change in potential energy. So it will be U final minus U initial and that will be 0. Clear? So work done in this process will be how much? In this process work done will be 0. बट अगर यहाँ पे मान लो कि ऐसा कुछ बोला गया होता कि डाइलेक्ट्रिक कांस्टेंट, डाइलेक्ट्रिक को बाहर में रख दिया जा रहा है, तो उस केस में हमारा कैपेसिटेंस जो होगा, दिस कैपेसिटेंस विल बिकम सी बाय के एंड दिस पोटेंशियल डिफरेंस विल बी हाउ मच? पोटेंशियल डिफरेंस इसको हम कैसे कैलकुलेट करें? भी इक्वल टू क्यू बाई सी। न्यू पोटेंशियल डिफरेंस विल बी हाउ मच? इट विल बी क्यू बाय सी। तो अभी इस वाले पर्टिकुलर केस में जो हमारा चार्ज यहाँ पे है, चार्ज यहाँ पे इसका वैल्यू कितना होगा? तो डाइलेक्ट्रिक को बाहर निकाल देने से थोड़ी ना चार्ज यहाँ पे चेंज होगा, ये एक आइसोलेटेड सिस्टम है। क्लियर? तो चार्ज विल रिमेन एज इट इज। तो चार्ज विल रिमेन एज इट इज मीन्स इट विल बी सी वी divided by c. So here in this particular case that charge will remain, that charge will remain as it is, that means previous value जितना था उतना ही रहेगा, but c का वैल्यू कितना है? इट इज c by k. तो c get cancelled, so finally how much will be getting? It will be k times b. तो पोटेंशियल जो होगा, न्यू पोटेंशियल डिफरेंस, दैट विल बी इंक्रीज्ड बाय k टाइम्स। तो अगर इंक्रीज हो रहा है यहाँ पे k टाइम्स, देन एनर्जी, what will be the value of energy? It will be half. So new capacitance is c by k, half c v square हमें करना है, तो it will be potential difference is k square into v square. So k will get cancelled out, so it will be half k c v square. क्लियर? तो ये वैल्यू हमें मिलता है यहाँ पे। तो अगर ऐसा क्वेश्चन हमें पूछा गया होता है कि अभी ये वाला सिस्टम ये फाइनल सिस्टम है और ये इनिशियल सिस्टम है। क्लियर? अंदर में डायलेक्ट्रिक मटेरियल है और उसको बाहर रख दिया जा रहा है, तो देन व्हाट विल बी द वर्क डन। तो वर्क डन इस केस में क्या होगा, इट विल बी हाफ के सी वी स्क्वायर माइनस हाफ सी वी स्क्वायर, और यू कैन से दैट इट विल बी के टाइम्स यू minus u. Clear? So finally here in this particular case it will be k minus 1 into u, or that value will be how much? It will be k minus 1 into half c v square. तो ये वैल्यू यहाँ पे हमें मिलता है। तो लेकिन ये वाला नहीं होगा, हमें यहाँ पे आंसर कितना मिल रहा है, यहाँ पे हमें 0 मिलेगा। अगर ये वाला प्रोसेस होता, क्लियर, तो उसमें हमें आंसर कितना मिलता, हमें यहाँ पे ये ऑप्शन बी जो है, ये दिस वुड बी द आंसर फॉर दैट केस। क्लियर? सो हियर इन दिस पर्टिकुलर केस रिमेंबर दैट प्रोसेस यहाँ पे हो रहा है कि हम डायलेक्ट्रिक मटेरियल को बाहर ले रहे हैं और फिर अंदर ले आ रहे हैं, बाहर लेके हम रख नहीं रहे हैं, ये वाला दिस इज नॉट द सिचुएशन ओवर हियर। क्लियर? तो इसलिए यहाँ पे आंसर यहाँ में कितना होगा, वाट डन विल बी 0। In this question, two identical capacitors have the same capacitance C. One of them is charged to potential V1 and the other to V2. The negative ends of the capacitor are connected together. When the positive ends are connected, the decrease in energy of the combined system is. So here in this particular case, what it is saying is that there are two capacitors. This is one capacitor which is having capacitance C, and it is having potential, let it be V1, and the other capacitor which is there is another capacitor here which is having capacitance C, and it is having potential V2. So these are the two capacitors which are present here, and the negative ends of the capacitor are connected together. That means here in this particular case, assume that this is the positive plate of the capacitor and this is the negative plate of the capacitor. Similarly here it is the positive plate and this is the negative plate. Clear? So negative end of the capacitors are connected together, negative ends are connected together over here. When positive ends are connected, so right now here in this particular case assume that these are not connected right now, so we'll connect them. Clear? The decrease in energy of the combined system. So we know that when we connect these two systems, so here in this particular case we assume that V1 is greater than V2, or we can assume V2 greater than V1. We can assume anything. So here in this particular case, if we assume V1 is greater than V2, then after connection what will happen? Redistribution of charges will take place. That means here initially in the upper capacitor charge is C V1, and in the means lower capacitor the charge is C V2. So when we'll connect them, then redistribution of charges will take place, and finally what will happen? Finally a particular point or particular time will come where when the potential of both the capacitors becomes same, then there will be no distribution of charges. Clear? So finally here in this particular case, so what we will be doing over here, so what is asking, what is the decrease in energy of the combined system? So in this particular case, so right now before connection, before connecting the positive ends, so before connecting the positive ends, what is the initial energy of the system? So initial energy of the system will be how much? So the upper capacitor, its energy will be half C V1 square, and the lower capacitor, its energy will be half C V2 square. Clear? So this is the energy. That means here in this particular case, what you can write, initial energy will be half C, we can take it common, so V1 square plus V2 square. And next one, suppose right now what we'll do the connection of this. Clear? So here in this particular case, if we do the connection over here, that means after connecting the positive ends. So after connecting the positive ends, what will happen? Redistribution of charges will take place, and both the capacitor will achieve common potential. So what will be the value of common potential? So common potential, let it be V. Here So what will be that value? Total charge divided by total capacitance. So it is nothing but total charge. Total charge is how much? So initially यहाँ पे चार्ज का तो रीडिस्ट्रीब्यूशन होगा. तो इनिशियली अभी ये जो सिस्टम है बिफोर कनेक्टिंग इनिशियल चार्ज लेट इट बी अपर प्लेट का जो चार्ज है, मान लो कि यहाँ पे Q1 होगा CV1 एंड Q2 का वैल्यू कितना होगा CV2. तो टोटल चार्ज कितना होगा? टोटल चार्ज Q विल बी इक्वल टू Q1 प्लस Q2 and that will be equal to C into V1 plus V2. Clear? So this will be the total charge before connecting the positive end. So after connecting here, as there is no external source, so these charges will get redistributed over here. That means there will be no loss of charges from the system. तो पूरा जो टोटल सिस्टम से चार्जेस का कोई लॉस या फिर कोई गेन नहीं होगा. तो टोटल चार्ज यहाँ पे कितना रहेगा? टोटल चार्ज, सो दैट विल बी टोटल चार्ज डिवाइडेड बाय टोटल कैपेसिटेंस. Total charge divided by total capacitance. So total charge we are getting C into V1 plus V2 all divided by total capacitance is C plus C, as both are having same capacitance. So that will not change. So finally how much we'll get? We'll get over here. So this is separate here. So finally the common potential that we'll get over here, that will be here in the denominator will be getting C2C. So it will be V1 plus V2 divided by 2. So this is the common potential. So if this is the common potential right now, that means after connecting what will be the potentials over here? After connecting, the new system will be having these potentials V and V each. Capacitance will remain as it is and potentials will be V each. So this is the new system after connection. Clear? So if this is the new system after connection, then what will be the energy stored over here? So it will be the final energy. So final energy in this particular system will be equal to half, here in this particular for the upper capacitor it will be half CV square, and for the lower capacitor it will be half CV square. So that means it will be CV square. So that can be written as C, but this V is nothing but V is the common potential. That means it can be written as V1 plus V2 divided by 2 whole square. So this is the final energy. Clear? After connecting or after the redistribution of charges. So right now what we'll do, we'll try to find out the loss. So here in this particular case, if we will try to find out the loss, that means loss of energy. And why we'll try to calculate the loss? Because it is asked to find out the decrease in energy of the combined system. तो वही loss के फॉर्मेट में हमें उसको कैलकुलेट करना है. तो loss of energy will be how much? So U initial minus U final. तो loss of energy को हम initial energy, as initial energy will be obviously greater than the final energy. So here in this particular case, how much loss will be there, that you can calculate U initial minus U final, and that should be always positive. ये हमेशा पॉजिटिव होना चाहिए, इसीलिए हमें इनिशियल से फाइनल यहाँ पे सब्ट्रैक्ट करते हैं. क्लियर? So initial energy is how much we got right now? We got this particular row. This is the initial energy, half C. It is half C V1 square plus V2 square minus final energy we got. We can write this one as C into, or you can what you can do over here, it will be C by 4 into V1 plus V2 square. So if we do calculations over here on this particular note here, if we do calculations, so let me do the calculations over here. So from here, that means what will be getting the loss of energy, it will be of the form this here. So it will be half. So what will here writing? So C by 2 V1 square plus 2 square, keep it as it is, minus it will be C by 4. Here this one is V1 square plus V2 square plus 2 V1 V2. Clear? So what we'll be doing, we'll be taking C by 2 outside. So it will be V1 square plus V2 square minus here half will remain. Clear? So half, if half remains, and if we multiply or if we open the bracket, so it will be minus V1 square by 2 minus V2 square by 2 minus 1. Clear? So this is what we'll get. So finally after that one we proceed ahead. So it will be C by 2. So V1 square minus V1 square by 2, it will be V1 square by 2 plus V2 square by 2 minus 1 V2. So or here in this particular case, if we take half common, so it will be C by 4. So it will be v1 square minus v1 square plus v2 square minus 2 v1 v2. So finally that one will be c by 4 into v1 minus v2 whole square. So that means the loss of energy will be how much? C by 4 into v1 minus v2 whole square. So that will be, that means here if you check C by 4 v1 minus v2, here it will be v1 minus v2 whole square. Clear? C by 4 into this is wrong, v1 minus v2 wrong, C by 4 v1 minus v2 whole square. So option C is correct. It is wrong. So this is the case. That means it is the process. It is a normal process through which we can solve this one. Clear? Or else what we can do, we can proceed with another method. We can proceed with another method, and what is that method? Is that to find out the loss of energy, we can use the direct formula. Loss of energy equal to half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. So as over here the capacitance are same for both capacitors, that is C. So this is the given information over here. Clear? So that means if we put these values over here, so how much we'll get? We'll get over here a loss of energy will be half C square divided by 2C into potentials, initial potential of both the capacitors are V1 and V2, that is same. So it will remain as it is. So V1 minus V2 whole square. So 1C will get cancelled over here. So we'll be getting C by 4 into V1 minus V2 whole square. So this you can get only when if you remember directly the formula for loss of energy, formula to calculate the loss of energy. ये अगर आप याद रखोगे तो डायरेक्टली आप इस फॉर्मूला को वहां पे अप्लाई कर सकते हो. In this question, the ratio of energy stored in a capacitor and energy dissipated during charging a capacitor with a source voltage is. So here in this particular case, what we just suppose if we look at the figure over here. So here in this particular figure, if we just see, this is a capacitor. Is a capacitor which is having some capacitance, let it be C over here, and this is a battery which is having some potential difference, let it be P. So that means this is a this battery is a source of energy. Clear? So here as this it is not connected over here, that means key is in open condition, so there will be no charging case. Clear? But once we connect it, that means once we close the key over here, then finally what will happen? Charging of capacitor will take place, and what will happen? So finally this as this left side of the plate is connected to the positive terminal, it will get positively charged, and the right one will get negatively charged. So it will get positively charged by plus Q, and this is negatively charged by minus Q. Clear? So that means over here in this particular plate finally some charges will appear. So what the theory says is that the left, that means as the left plate of the capacitor is getting positively charged over here. Clear? That means what the theory says is that this battery which is present over here, what does it take? What does it do? It takes the positive charges from the right plate to the left plate. Clear? Throughout this particular path, or else we can say that it takes the negative charges from the left plate से negative charges यहाँ पे ऐसे लेके यहाँ पे right plate तक देता है. Clear? So that means anyhow magnitude wise some charges is transferred, and how much charge is transferred over here by the source of energy or by the battery? Suppose Q amount of charge is transferred. Clear? So here in this particular case work done by the battery will be how much? That will be simply Q into B. We know the formula because that Q amount of charge when it is moved through a potential difference of V volts, then energy or work done will be how much? It will be QB. But here this Q amount of charge is transferred to the capacitor, and it is stored in the capacitor. Clear? And due to which the capacitor will gain some energy. Clear? So here in this particular case the energy of the capacitor, energy of the capacitor will be how much? So it will be half C V square. energy of the capacitor is how much? It is half C V square, another formula, or else we can write it will be simply Q square by 2C, or else we can write half QB. Clear? So if the potential is this is a connection where that means this capacitor will get charged up to what? Up to having a potential difference of V volts, same as the source potential. So that means here charge obtained is Q and potential difference is V. That means energy across the plates of the capacitor will be how much? Half QV. So here in this particular case, so this is the work done by the battery or work done by the source. Clear? That means this much energy is utilized by the source to move that Q amount of charge, and but finally how much energy is achieved or how much energy is gained by the capacitor. कैपेसिटर में फाइनली कितना एनर्जी आ रहा है? हाफ क्यू भी, बट उसको एनर्जी वहाँ पे एनर्जी जो हम यहाँ पे चार्ज के फॉर्म में जब स्टोर कर रहे हैं उसमें फाइनल जो एनर्जी आ रहा है उसके लिए बैटरी जो है वो कितना काम कर रहा है? क्यूबिक अमाउंट का एनर्जी वो यूटिलाइज कर रहा है. क्लियर? तो फाइनली लॉस ऑफ एनर्जी कितना हुआ? मतलब यहाँ पे पहले 1 था और अभी हाफ हो रहा है, तो कुछ एनर्जी लॉस हो रहा है. क्लियर? सो लॉस ऑफ एनर्जी, loss of energy will be how much? It will be half QP. Clear? So this is what it is asking, the ratio of energy stored in the capacitor, which is half QB, and energy dissipated during charging. So during charging how much energy is dissipated? So that energy is nothing but same energy. Clear? So what will be the ratio of these two? So ratio of these two will be 1:1. तो इन दोनों का रेशियो, नॉट दिस वन. क्लियर? इन दोनों का लॉस ऑफ एनर्जी और यहाँ पे एनर्जी ऑफ कैपेसिटर जो है उनका जो रेशियो होगा वो कितना होगा? 1:1 रेशियो. तो ऑप्शन ए विल बी द करेक्ट वन. इन दिस क्वेश्चन, two capacitors 3 microfarad and 4 microfarad are individually charged across a 6 volt battery. After being disconnected from the battery, they are connected together with the negative plate of one attached to the positive plate of other. What is the final total energy stored? So here in this particular case, if you just look at the figure over here, suppose here in this particular case two capacitors, assume that this is 3 microfarad and this is 4 microfarad capacitor. Clear? So these are separately connected across 6 volt battery. Clear? And right after that means suppose assume that it takes some time and within a fraction of second both the capacitors separately they are charged. So here in this particular case, the charge across this capacitor, let it be Q1, and let the charge over here is Q equal to CV. So that means 3 into 6. So that will be how much? 18 microcoulomb. Clear? And similarly charge over this particular capacitor will be, let it be Q2, then that will be C into V, that means 4 into 6, so that will be 24 microcoulomb. Clear? So that means the charges across both the capacitors separately we are getting 18 and 24 microcoulombs. So right now after what they are saying is that these two capacitors which are disconnected from the battery and they are connected together, here they are connected over here. So assume that here this is 3 microfarad capacitor and here it is 4 microfarad capacitor with negative plate of 1 attached to the positive plate of 1. That means here the positive plate of 3 microfarad capacitor is connected to the negative plate of 4 microfarad capacitor, or we can say the positive plate of 4 microfarad, negative plate of 3. Previously what we used to do is that here in this particular case, obviously the connections means when two capacitors, charged capacitors are connected to each other, that in that particular case actually how they are connected, so both positive terminals are connected together and negative terminals are separately connected together. Clear? So positive connection and negative connection. So here in this particular case, what will be the total charge? Total charge will be nothing but simply what we'll be doing. So here in 3 microfarad capacitor, the total charge is 8 coulomb. That is 4. So when the total charge particular when positive of one plate, total charge right. So micro be how much? It will be 18 plus 24. So that will be approximately 42 microcoulomb. Clear? So that total charge, calculation of total charge is helpful while finding out the common potential. Why? Because in both the connections, here in both the connections, what will happen? Finally, redistribution of charges will take place. Clear? In both the connections, and redistribution means finally what will happen? Finally, both the capacitors will achieve same potential. Clear? Finally, what will happen? Both the capacitors will achieve same potential. That means we can find out the common potential over here. So common potential. So how will you calculate the common potential over here? So here in this particular case, if we want to calculate the common potential, and that will be, so common potential, let it be V over here. So if common, that means it will be nothing but total charge upon total capacitance. It will be total charge upon total capacitance. So what is the total charge here in this particular case? We got right now, it is 6 microcoulomb divided by total capacitance is how much? Total capacitance, whether you connected positive to positive or positive to negative, in any case the total capacitance will be simply means just add the capacitance of individual capacitor. Clear? So total capacitance will be sum of individual capacitance of both the capacitor, that is 3 plus 4, that will be 7 माइक्रोफैरड. तो दोनों कैपेसिटर्स को हम ऐड करेंगे तो हमें 7 माइक्रोफैरड यहाँ पे मिलेगा. तो फाइनली that 6 microcoulomb can be written as 6 into 10 to minus 6 coulomb, and 7 microcoulomb will be 7 into 10 to minus 7 farad. So 10 to minus 6 in the numerator and denominator will get cancelled out. So finally it will be 6 upon 7 volt. Clear? So here why we have taken here why, that means the reason behind over here is that when positive is connected to the negative, that means here the potential generally decreases. Clear? So here what will happen? The potential generally decreases, and that value of common potential that we are getting over here is 6 by 7 volt. Okay, so if it is the common potential, then what it is asking? It is asking to find out the final total energy. So total final energy कितना होगा? Clear? So total final energy of this combined system, it will be how much? It will be half C V square. Half C V square, that means here for 3 microfarad capacitor, its capacitance into potential difference, that means the common potential, as both capacitors are having common potential. That means here this capacitor is having 6 by 7 volt of potential, this capacitor is also having 6 by 7 volt of potential. So that means the final total energy can be written as final total this is 6 by 7 volt. Okay, so half we can write this is capacitance of the capacitance, we can write over here, or directly we can write simply, no need to write the individual cases. So for the upper capacitor, it will be 3 halves 3 microfarad. So 3 into 10 to the power minus 6 farad into potential difference is 6 by 7. 6 by 7 square. Then next plus the capacitor, which is the lower capacitor, which is having energy of that means half CV square. It will be 4 into 10 to the power minus 6 into potential across the capacitor will be taken as common potential, so 6 by 7 whole square. So here in this particular case, if we take half into 6 by 7 whole square common outside, so half into, so this will be 3 plus 4, so 7 into 10 to the power minus 6 into 6 upon 7 square. So 6 square is 36 and 7 into 7, let it be. So this 7 and 1 7 will get cancelled out. And here it is 18. So it will be 18 upon 7. 18 upon 7 into 10 to the power minus 6 joule. So 18 upon 7, if we do the calculation, so we'll be getting, so 18 upon 7, so 7 to the 14, so 4, so it is 5, 35, so 5, 7, so 2.57, 2.57 into 10 to the power minus 6 joule. Clear? So so the value will be option A wrong, option B 10 to the power minus 4 joule wrong, here C, and D the 10. So option D will be the correct one. In this question, a parallel plate capacitor without any dielectric within its plates has capacitance C. So there is a parallel plate capacitor, assume that, and here without any dielectric inside it. So its capacitance is how much? Capacitance is C, and is connected to a battery of EMF V. So here this capacitor is connected across a battery of potential difference is how much? V. So that means this capacitor will achieve will get charged till having the potential difference same as the source, that means V. The battery is disconnected and the plates of capacitor are pulled apart. So here in this particular case, so here what we'll do, so this battery is disconnected, so we are disconnecting the battery from here. Clear? And right after that, what it is done over here is the capacitors are pulled apart until the separation between the plates is double. So right now here in this particular case, the capacitor, so here if we take this particular capacitor over here, this capacitor, the separation between them is doubled. So here in this particular case, the separation between them is we are making double. So here initially it is, let it be D, then here the distance between the plates will be 2D. Okay, so what it is asking, what is the work done by the agent pulling the plates apart in this process. So here in this particular case, work done, that work done is generally in the form of energy. Clear? So that means, so we will calculate the initial energy and final energy, and after that we'll check what is the work done. So what is the initial energy here in this particular process? So in this particular case, when the battery was connected over here, then energy is, initial energy will be nothing but half C V square. We could have used another other formulas, Q square by 2C or half QB, but here options are given in the form of CV square. So that means we will be using this formula of energy. So energy here, initial energy of the capacitor will be half CV square. And after this one, what will happen? So that means here in this particular case, the capacitor is charged by Q. That means here positively charged, and here this is negatively charged plate. So that means charge of the capacitor plate is Q, and the value of that Q is how much? That value is CV. Clear? So that means after disconnecting, still which one will remain same? So the charge across the plates will remain same. So that means positively charged, this will be negatively charged. Clear? Plus Q and minus Q. So if charge remains constant according to the law of conservation of charge, so that means which one will change? Capacitance will change as the distance between the plate is changing. Even though the area is constant, डिस्टेंस यहाँ पे चेंज हो रहा है, तो इसलिए यहाँ पे कैपेसिटेंस चेंज होगा. तो कैपेसिटेंस यहाँ पे कितना होगा? सो लेट द कैपेसिटेंस भी सी प्राइम. सो सी प्राइम यहाँ पे इसका वैल्यू कितना होगा? इट विल बी एप्सिलॉन नॉट ए डिवाइडेड बाय डिस्टेंस बिटवीन द प्लेट्स इज 2d. बट हियर इनिशियली the capacitance of this one will be how much? Simply epsilon naught A by D. So that means here we can write it will be C by 2. The new capacitance will be C by 2. And similarly, what will the potential difference across the plates? Then potential difference we can write it over here. Let it be V prime. So V prime will be equal to Q by C prime. So it is Q by C prime. So here in this particular case, what is the value of Q? Q will be same as the previous one, so it will be CV divided by C prime. It's C by 2. So C will got cancelled, so it will be 2B. So new potential difference across the plates will be 2V, which is increased. So that means here in this particular case, what is the final energy we'll get? So half C prime V prime square. So half C prime is C by 2 and V prime is 2V square. That means it will be 4V square. So 4 will get cancelled, so it will be CV square. So this is the final energy. So this is the final energy, and initial energy is half CV square we got just right now. So that means what is the work done during the process? So work done will be nothing but final energy minus initial energy. Clear? Final energy to final energy of the system minus initial energy of the system. So it is CV square minus half CV square. It will be half CV square. So the work done during the process will be how much? It will be half CV square. That means option A will be the correct one. In this question, a series combination of N1 capacitors, each of value C1, is charged by a source of potential difference 4 volt when another parallel combination of N2 capacitors, each of value C2. So that means here they have given N1 capacitors which are connected in series, which are having capacitance of C1, and similarly there are N2 numbers of capacitors having each capacitance C2, and they are connected in parallel. So here that means combination of something N1 and N2 numbers of capacitors. Clear? So here in this particular case here N1 numbers of, that means here N1, here it is N1 numbers of capacitors are present over here, having, and each capacitor is having capacitance of C1, 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 C1. Clear? And this in this series combinations, that means series combination of N1 number of capacitors across a potential difference of 4 volt, across a battery of 4 volt, and there is a combination of N2 numbers of capacitors which are having capacitance C2, C2, C2 and C2. That means it is N2 numbers. Clear? Across a potential or battery of potential difference V over here. Clear? This is positive, negative, positive, negative. Okay. And what it is saying that after doing all these things, they have, or you can say it has the same total energy stored in it. That means both of the systems are having same energy as the first. That means this second one has the same energy stored in it as the first combination has. The value of C2 in terms of C1. So here what it is asking, it is asking to find out the value of C2 in terms of C1. So here in this particular case, we know the formula for energy U equal to half CV square. So here in this particular case, if we can calculate the equivalent capacitance of series and parallel combinations, then we'll get the energy over there, because potential difference we know that one. So here in series combination, so particularly in series combination, equivalent capacitance will be how much? So n numbers of equal capacitors are connected in series, n1 numbers. That means equivalent capacitance will be how much? Simply C1 divided by n1. Why? Because 1 by CS will be nothing but 1 by C1, 1 by C1 plus 1 by C1 plus 1 by, ऐसे हमें n1 numbers टाइम हमें ऐड करना है. क्लियर? तो उसका मतलब है कि ये कितना होगा n1. दैट मीन्स हियर इन दिस पर्टिकुलर केस CS विल बी C1 by n1. क्लियर? ये वैल्यू कैसे मिला हमें? ये वैल्यू हमें ऐसे मिलेगा 1 by CS इक्वल टू 1 by C1 plus 1 by C1 plus 1 by C1 so on up to plus 1 by C1. तो मतलब ये n नंबर टाइम्स यहाँ पे ऐड हुआ है. क्लियर? तो दैट मीन्स दिस विल बी हाउ मच? 2 होगा तो 2 by C1, 3 होगा तो 3 by C1, तो n1 होगा तो ये कितना होगा? n1 by C1. So that means the value of CS will be how much? The value of CS will be this one, C1 by n1. Clear? And so if this is the series combination of n1 capacitors. Clear? So if this is, and the potential difference is how much over here? It is 4 volt. Then energy in series combination will be how much? Half CS into V square, means voltage across series combination, so Vs square. So half CS is how much? CS we are getting this one, C1 by N1. So CS we are getting how much? C1 by N1. This is the value what we are getting. So it is C1 by N1 into Vs. Vs is 4 volt square, that means 4 square. It will be simply 4 square. So how much will be getting? No need to write 4 whole square because you will get confused. So it will be 4 square. So how much will be getting? We'll be getting 16. So 16 by 2, that is 8. So 8 8 C1 upon N1. So energy in series. Energy in series, what we are getting? 8 C1 by N1. So similarly over here, what we'll be doing? We'll be doing for the parallel. For parallel combination, what will be the result over here? So here in this particular case, we can see that n2 numbers of capacitors are connected in parallel. That means equivalent capacitance will be in that means C2 plus C2 plus so on up to plus C2. तो ये n2 numbers times है, तो that means 2 होगा तो 2C2, 3 होगा तो 3C2, that means n2 होगा तो it will be how much? n2C2. That means Cp is how much? It will be n2C2. That means its energy across the parallel combination will be how much? Half C Vp square. But here Vp is how much? Vp is V, because this is the potential difference across all that means this across this combination. तो यहाँ पे ये वाला पर्टिकुलर केस में ये कितना होगा? हाफ Cp is n2C2 and here Vp is simply what you can say, it is potential difference is V here 4V. okay, 4V, that means we can write that one. okay, no problem. So 1, that means इसको हम एज्यूम कर लें कि 1 वोल्ट, या फिर इसको V ही एज्यूम कर लो, सबसे बेटर होगा. तो ये 4V स्क्वायर होगा, मतलब ये 16V स्क्वायर. सो दैट विल बी, लेट इट बी V स्क्वायर. हमें यहाँ पे V स्क्वायर ले जाना है. क्लियर? तो ये V स्क्वायर यहाँ पे होगा. क्लियर? ओके, 4 पोटेंशियल डिफरेंस यहाँ पे 4 वोल्ट यहाँ पे नहीं लेना है, इसको 4V लेना है और यहाँ पे इसको V लेना है. ठीक है? So n2C2 into Vp square, that means it will be V square. Clear? So this is what we are getting the energy in parallel combination. And finally what it is saying, it is saying us that these two energies are equal. That means US equal to UP. That means here we can say that 8C1 upon N1 V square equal to half n2C2 V square, as both V square will get cancelled out. So finally here in this particular case, what is asking over here, if you just look at the value of C2 in terms of C1, that means value of, what is the value of C2? So value of C2, if we just calculate over here, that means C2 will be nothing but 2 will go to the numerator side. That means we'll write first the left hand side part on the right hand side over here. That will be 8 1 upon N1, and 2 will go to the numerator into 2, and here N2 will go to the denominator here divided by N2. So it will be 16 1 upon 1 N2. So the value of C2 in terms of C1 will be how much? 16 upon 1 N2 into. So this will be the value of C in terms of C1. 16 upon N1 N2. 16 upon N1 N2 to C1. So option D over here will be the correct one. Clear? In this question, what is the energy stored in the capacitor between terminals A and B of the network shown in the figure? So here it is terminal A. Let me indicate it here. This is terminal A and this is terminal B. That means it is asking about what is the energy stored in this particular capacitor. Clear? In this particular, here this is the capacitor. Clear? And capacitance of each capacitor is 1 microfarad. So here in this particular case, if we just arrange arrange this particular arrangement which is given over here, so if we do rearrangement of this one, so let the points or terminals over here are, suppose if we take the terminals over here, suppose this is A and this is B and this is E and this is T. Clear? So here between A and B there is one capacitor, and this is the capacitor which is between A and B, and between B and E, this is the capacitor. Clear, this particular one. So here between B and E, this is the capacitor. And similarly between D and E, so if we just look at D, this is D and this is terminal E. So between D and E, this is the capacitor which is connected between them. So another capacitor, this one, and last one between A and D. So if we check, so this is terminal A and here, so this will be A. So finally between A and D, there is another capacitor which is this one. So finally this is the connection and 4 connections. And what is there any capacitor between B and D? So let's check between B and D. Yes, this is the capacitor which is between B and D. So this is the capacitor which is between B and D. Clear? Okay. So is there any connection between A and D? So this is A. So that means this will be A. So A. So this is A. And here this is E, this is E. So finally between A and E there is a cell of potential difference. How much? Potential difference of 10 volt. Here, so this is 10 volt. So here this arrangement is something looks like it is a kind of Wheatstone bridge. Here it is forming a Wheatstone bridge. Clear? So Wheatstone bridge, just like for example how the Wheatstone bridge looks like. So here, case of Wheatstone bridge, what they do is that instead of the capacitors, they used to take the resistors. Here instead of the capacitor, so what they used to do, they used to take resistors over here. Here there will be a resistor. Here also you will get one resistor. Here another one resistor, and here this is one resistor. So here resistors are there. So let the resistance be R1, R2, R3, R4, and let it be this is a resistor which is same as the resistance of galvanometer. Clear? So what actually happens is that if this forms a Wheatstone bridge, then net current through this galvanometer will be 0. So no current through this particular one. Clear? So that means here in this particular case, if this bridge satisfy the Wheatstone bridge condition, then we can write R1 into R4 will be equal to R2 into R3. Clear? So this is the condition, or else we can write R1 by R2 equal to R3 by R4. Clear? But we are not going to apply this particular condition over here. So this is the case of Wheatstone bridge. Similarly, this is Wheatstone bridge of capacitors. Clear? So this is Wheatstone bridge which is of resistors. It is of capacitor. That means here also there will be no charging of this particular middle capacitor which is connected between B and D. So that means finally what will happen, as we can see, as there will be no capacitor over here. So this capacitor arrangement system, how it will become, so there will be no capacitor over here. Clear? That means no capacitor. So if it is if there is no capacitor, that means what we can say, so no capacitor, that means here as this is connected across the cell of 10 volt potential, that means the current will flow through it like this. So these two capacitors will be in series and this bottom two capacitors will be in series, as this is of 1 microfarad. Each capacitor is of 1 microfarad each capacitor is of 1 microfarad each. So here it is also 1 microfarad and it is also 1 microfarad. Clear? That means what we can what it is asking, the energy stored in the capacitor between the terminals A and B. So it is asking what will be the energy stored in this capacitor here, this particular one. Clear? So here we can say that the potential difference across this is parallel combination. These 2 microfarad capacitors are in series, so their equivalent capacitance will be half microfarad, and these two are in series, so their equivalent capacitance will be half microfarad, and these half microfarad capacitors are in parallel. That means the potential difference across this upper two capacitors will be 10 volt, and the potential difference across the lower two capacitors will be of 10 volt, clear, as they are parallel, as they are in parallel. That means the potential difference across this 1 microfarad will be how much, or potential difference across this 1 microfarad will be how much, as they are having both capacitors, दोनों कैपेसिटर जो यहाँ पे प्रेजेंट है ऊपर में, दोनों का कैपेसिटेंस सेम है, तो पोटेंशियल डिफरेंस यहाँ पे क्या होगा सीरीज केसेस में, यहाँ पे ये हो जाएगा 5 वोल्ट और ये हो जाएगा 5 वोल्ट, क्लियर. सिमिलरली हियर पोटेंशियल डिफरेंस विल बी 5 वोल्ट and here also it will be 5 volt, clear, but we don't need to calculate the total energy of each capacitor. So here it is asking the energy stored in this particular capacitor only. So this capacitor is having capacitance 1 microfarad and potential difference across that one is 5 volt. So that means what will be the energy stored? Energy stored will be equal to half CV square. So half capacitance is 1 microfarad, so 1 into 10 to the power minus 6 farad into potential difference is how much, 5, potential difference is 5, so here 5 square, so finally how much will be getting, so it will be 10 to the power minus 6 into 25 by 2, that means it will be 12.5, so 12.5 into 10 to the minus 6 joule, clear. So that means what you can write, it will be 12.5 microjoule, so it will be will be getting, so it will be 12.5 micro, clear. So this will be the answer. So we can check the options over here. So first option is 12.5 microjoule, that is correct. Wrong, so this is wrong, so this is also wrong. So here option A will be the correct one. In this question, consider a parallel plate capacitor with plates 20 cm by 20 cm and separated by 2 mm. The dielectric constant of the material between the plates is 5. The plates are connected to a voltage source of 500 volt. The energy density of the field between the plates will be close to. So here in this particular case, what the information that is given over here. So the plates, suppose these are two parallel plates which are having, or here in this particular case its sides are 20 by 20, that means these are square plates, clear, and separated by 2 mm distance, clear, separated by 2 mm distance, and inside the given plates, suppose there is a dielectric material which is present over here. Suppose assume that this is a dielectric material which is present in between the plates, clear. This is the material which is present in between the plates. Okay, so this material is of dielectric constant K equal to 5, clear. And these plates are connected across a source of how much, a source of 500 volt, clear. So what is asking, the energy density of the field between the plates will be, clear. So here in this particular case we know that the formula for energy density U, small u, that will be equal to half epsilon naught E square. That means it is the energy per unit volume. Energy density, how do you define the energy density? It is nothing but it is the energy per unit volume, clear. So if it is the case, then what will be what will be that value? So here it will be half epsilon naught. Epsilon naught is how much? Epsilon naught is 8.85 into 10 to the power minus 12. And E, electric field. What is the electric field between the plates of capacitor, clear, with dielectric being inserted. So here in this particular case, as we are applying a potential difference of 500 volt across the plates which are having separated by a distance of 2 mm over here. So that means here potential difference V equal to E into D, or E equal to V by D. So potential difference is 500 divided by distance between them is 2 mm, so 2 into 10 to the power minus 3. So that will be approximately 250 into 10 to the power 3, or we can write that one as 25 into 10 to the power 4, clear. So 25 into 10 to the power 4 volt per meter. This is the electric field between the plates, clear. So if it is the electric field between the plates, that means what we will be getting, we will be writing E square, that means 25 into 10 to the power 4 whole square. So after doing the calculation, so that will be, so it will be half into 8.85 into 10 to the power minus 12 whole into 25 square, that will be 625 here, or we can keep it like that. We'll be keeping it like that, so it will be 25 into 25 into 10 to the power 8 here. Okay, this is the energy per unit volume. Okay, here in this particular case, okay, here we have forgotten to keep the dielectric constant over here. So here in the energy density, as we know that when the source is connected to the capacitor plates and the dielectric is inserted, then energy stored across the plates will increase by k times. Clear? So it will increase by k times. That means here k is how much? K is 5. So here in this particular case we have to multiply 5. Clear? So it is 5 into epsilon, it is 8.85 into 10 to the minus 12 into this much. Clear? So here it will be 5 will be there, so it will be 5 into this one. Okay, so okay, this is what we are getting. So finally here we can write over here, so we can write this is 2.5, so it will be 2.5 into 8.85 into 25 into 25 into here 10 to the minus 12 and 10 to the 8, so it will be 10 to the power minus 4. And if we take this 10 to the minus 4 to the denominator, so it will be 2.5 into 8.85 into 25 into 25 whole divided by 10 to the 4 means 10 to the 2 into 10 to the 2, that means it is 100 into 100. So it is get cancelled out by 4. Here it is also 4. And finally here in this particular case, let it be so finally how much we are getting? We are getting here we can write, so finally 2.5 into 8.85 divided by, let it be 2 into 8. Clear? So here it is, we can cut it by 1.1. Clear? So here we can also do what here in this particular case, if we take, so 2.5 into 1.1 divided by 2, 2.5 into 1.1 divided by 2, I think we're something so how much will, okay, approximately we can get let it be in this calculation, suppose if we'll remove the decimals, so if we remove the decimals, so how much we'll get, so it will be approximately we'll be getting 25 into 11, 25 into 11 divided by 2 into 100. Here, so 25 into 11, that means here it will be 25, so 5, 7, here it is 2, so it will be 275 divided by 2 into 100, so approximately 2 ones are 2, then 2 3s are 6, then 2 4 2 3 6 6, that means 1 is remaining, so 2 7s are, it will be 2 7s are 14, then 1 remaining, so dot, so something around 137, so around 137 will get, so 137 divided by 100, so that will be approximately 1.37. Clear? So that will be how much? That will be approximately 1.37. So this is what will be the energy density. That means energy, as we are calculating the energy per unit volume, we are applying the formula for energy per unit volume, so that means it will be joule per meter cube. So finally it is 1.37 joule per meter cube. So we'll check the answers. So option A 2.65 wrong, 1.95 wrong. So option C 1.38. That will be nearly approximate value, and option D is also wrong. So option C will be the correct one. In this question, total energy stored in the condenser system as shown in the figure here. If you just look at the figure, then this 6 microfarad capacitor and 3 microfarad capacitor, these are connected in series. Clear? As these are connected in series, that means their equivalent capacitance will be it will be 6 into 3 divided by 6 plus 3, so it is 18 divided by 9, so it will be 2 microfarad. Why? How we are getting 2 microfarad? Because the formula that we have applied over here is C1 into C2 divided by C1 plus C2. Clear? This formula we have applied. So by applying that one, how much we are getting? We are getting 2 microfarad. So suppose we are getting 2 microfarad capacitors. So this is 2 microfarad. So here in this particular case, what we'll be doing? We'll be removing these two. Clear? So here there is no capacitors. Assume that no capacitors are present over here. Clear? So finally, even think that this wire is also not there. Clear? So we can remove this wire. We can disconnect this wire also. Clear? So right now here in this particular case, these 2 microfarad capacitors are connected in parallel. Okay? So these 2 microfarad capacitors are assumed to be connected in parallel. That means their equivalent capacitance will be how much? Their equivalent capacitance will be, so it will be 2 plus 2, that means 4 microfarad. So their equivalent capacitance will be 4 microfarad. That means over here we can further, right now what we can do, we can remove these two. Clear? So here we can remove these two. So this is not there. So that means this is of how much? This is of 4 microfarad. That means this 2-volt battery or cell is connected across a 4 microfarad capacitor. Then what is asking? What is the total energy stored? Total energy will be half. Energy stored will be half C V square. So half into capacitance is 4, and potential difference is how much? It is 2 volts. So that means 2 square. Clear? So 1 2 1 2 will get cancelled out. It will be 8. 8 how much? 8 into 10 to the power. Here it is capacitance is 4 microfarad. So 4 microfarad means we have to write 10 to the minus 6 farad. So 10 to the minus 6 will remain as it is. So here finally what we'll get? We'll get 8 into 10 to the minus 6 joule, or that can be written as 8 microjoule. So that's why I have not written that 10 to the minus 6 over here, because we know that here after multiplication we will get the result in terms of microjoule. Clear? So option A here is given the answer. So that means option A will be the correct one. In this question, a capacitor with capacitance 5 microfarad is charged to 5 microcoulomb. So here initially this is a capacitor. Its capacitance is, assume that its capacitance is 5 microfarad. Clear? And this capacitor is charged by connecting some sources. So let its charge given over here is 5 microcoulomb. This is the initial capacitance and initial charge of the given capacitor. If the plates are pulled apart to reduce the capacitance to 2 microfarad. So here the same capacitor we have taken over here, but what we are doing right now, according to the given information, we are pulling apart. We are pulling the plates. That means we are increasing the distance between the plates of the capacitor. So when they are pulled apart, the new capacitance over here is 2 microfarad. Clear? And then the question is that what will be the charge? As this is an isolated system, it is not connected to any other system. That means charge will remain constant. Clear? According to the law of conservation of charge. Clear? So here in this particular case, what it is asking, how much work is done. So here what is the energy in the initial case? In this particular situation, the energy is U initial will be equal to half CV square. So half, or else we can apply the other formula. Because charge and capacitance is given, that means we can use the formula of Q square by 2C. So that means Q is 5 microcoulomb. So 5 into 10 to the power minus 6 whole square divided by 2C means 2 into 5 into 10 to the power minus 6. So this initial capacitance will be how much? Initial capacitance will get so it is 25 into 10 to the power minus 12 whole divided by we can write over here, this is 10 into 10 to the power minus 6. So here we can cut that one, so we'll get 2.5, and this one will be how much? It will be 2.5 10 to the minus 6 if it goes up, so it will be 2.5 into 10 to the minus 6 joules of energy. So the initial energy across the capacitor is how much? 2.5 into 10 to the minus 6 joule. And similarly, when the capacitor plates are pulled apart, then in that particular case, what will be the energy? So energy over here. So energy over here, let it be U final. So we'll be using the formula half CV square. So half into capacitance is 2 into 10 to the power minus. Okay, so here we'll not be using that one. So we'll be using the formula of Q square by 2. So it will be Q square by 2C. Clear? Because we know the value of charge over here, we know the capacitance, so why not we use this one? So it will Q square, that means 5. It will be same 5 into 10 to the power minus 6 whole square divided by 2 into capacitance is 2 microfarads, that means 2 into 10 to the minus 6 farad. Clear? So finally over here, if we do the calculations, so it will be 25 into 10 to the power minus 12 divided by, it will be 4 into 10 to the power minus 6. So 25 upon 4. So 25 upon 4, that means it will be 25 upon 4. So 4, 6 is 24. So 1 remaining. So here put the decimal over here. So 2, 4, 2 is 8. So it is 2. So it is 0. So 6.25. So it will be 6.25. 10 to the 6 goes up. So it will be 10 to the minus 6. So finally, final potential energy U final, how much we are getting? 6.25 into 10 to the power minus 6 joule, or it will be 6.25 microjoule U final, and here U initial is how much? 2.5 microjoule. Clear? This is the initial energy. So then what done? Work done. It is asking about work done. So work done will be how much? U final minus U initial. So it is 6.25 minus 2.5. So that will be, means how much will be getting? 6.25, and here 2.5. So 5 will goes here. So here 12. So it is 7. So 5 is there. So in the end, so finally 5 minus 2, that is 3.75. So how much will be getting? Will be getting 3.75 microjoule. Clear? So this will be the work done. Work done will be 3.75 microjoule, or else here 3.75 into 10 to the minus 6 joule. So 3.75 into 10 to the power minus 6 joules of work will be done. We can check the option. 3.75, option B, 10 to the minus 6, correct, wrong, and wrong. So option B will be the correct one.